This presentation aims to analyze an article named Dynamo, Amazon's highly available key-value store. Dynamo derives from dealing with the problems of traditional relational database system, including expensive hardware support needed, high demands for personal skills of programmers. The emphasis on strong consistency is higher than availability, and the increase in availability is constrained. Performance scaling and clustering are limited by the complexity introduced by various capabilities. Dynamo therefore adds a set of storage implementations designed for these issues, giving up the ability to model data, complex queries, transaction management, and choose a strategy with higher availability than consistency. More specifically, what is Dynamo? First, it's a highly available, high-performance data store from Amazon. Second, it gives up the ability to model data, and all data objects are stored using the simplest key-value model. Third, it sacrifices partial consistency in exchange for high availability. On one hand, there are three main disadvantages of Dynamo. For query model, Dynamo is limited to key-value queries and positioned to store relatively small data objects, typically less than 1 MB, without supporting operations or relational operations across multiple pieces of data. Also, compared to the traditional relational management database, Dynamo weakens consistency and does not provide any guarantee of isolation. For security part, Dynamo anticipates that the runtime environment is trustworthy and does not provide any security mechanisms, such as usernames and passwords. On the other hand, one of the advantages of Dynamo is efficiency in terms of strict latency requirements to meet SLA guarantees. Namely, 99.9% response time is 300 milliseconds at the client's 500 request load spikes per second. Besides, it can flexibly add some storage hosts to improve the system's service capabilities. Moreover, the system uses a P2P architecture, and each node is peer-to-peer and has the same responsibility. Since each node in the system is peer-to-peer, when the same data item is written concurrently, the data of each node may be inconsistent. Now, let's move on to the application of Dynamo in Amazon. Considering Amazon's business scenario, Amazon operates an e-commerce platform that serves tens of millions of users simultaneously. Even short-lived unavailability, such as write rejection, can result in lost transactions and poor user experience, which is too costly for a business platform with a large user base. So the system must be strong, highly available, and sacrificed. There is only consistency, a strategy for ensuring the ultimate consistency of Dynamo's sacrifice in the commercial environment has been proven to be feasible. The practical utilities contain bestseller list, shopping cart, session management, and etc. Next, the essential techniques will be explained.
So there are several techniques used in Dynamo. For the system interface, Dynamo stores objects associated with the key through two operations, get and put. Basically, get method will return the object associated with the given key, and put method will determine where the object should be stored. It's just like an Amazon online phone market. The get method refers to customers looking for information of phones, and put method would likely to be managers changing prices of their phone products. As we mentioned before, one of the crucial requirements for Dynamo is the scalability. To achieve this, the system used a variant of consistent hashing. In consistent hashing, each node on the ring would only be responsible for the region between itself and its predecessor node. While in the variant algorithm we're actually using, each node can be responsible for more than one successor node, and these successor nodes are the so-called virtual nodes. There are several advantages of using virtual nodes. Like the system could receive fault tolerance, it would be easier to scale out, and there would be more flexibility of choosing the number of virtual nodes. The other crucial requirement for Dynamo is the high availability and durability. Like our phone market example, if customers can't search phones or buy phones with the fear of only one node or several nodes, it actually doesn't make any sense. so Dynamo makes replicates for its data to deal with this. For one system, each single piece of data is replicated at n host, and n here is nothing more but a parameter configured per instance, which indicates the number of hosts that our data will be replicated at. Therefore, for each host, it will replicate data between itself and n former hosts. For example, in this system, let's assume n equals to 3. So for our host B, it will replicate data between itself and 3 former hosts, which is A, G, and F. Basically, host B is going to store data between AB, GA, and FG. But what happened to a specific data? Once a key is going to be stored in the system, it will be assigned to a coordinate node, and this node will be in charge of the replication of this key. In addition to locally storing each key within its range, the coordinator replicates these keys at the n-1 clockwise successor nodes on the hash ring. As is shown in this video, once the key k is going to be stored in the system, it will be firstly assigned to the coordinate node, which is B, and node B will replicate k to the following 3-1 nodes, so eventually key k will be stored in all B, C, and D. Then it's quite obvious that once the system is designed, we would already know which nodes would be responsible for storing a particular key, so we call the list of nodes the preference list of the certain key. Now let's see the process of adding or removing nodes, which is what we do in reality to scale out the system. Once a new node, say X, is added into the system, it will get assigned to a number of random virtual nodes in the ring. Since the new node X is added, some existing nodes no longer have to store some of their keys. Basically, what happened here is that this node will transfer those unnecessary keys to X and remove these keys from their local sites. Much of the same for removing. When a node is removed from the system, the reallocation of keys happens just in a reverse process.
Dynamo uses asynchronous replication because we know synchronous replication will take a long time for waiting other nodes' response. So far, Dynamo is just like a normal distributed database, so how does it to overcome some specific amazing requirements such as to be an always writable database? In our example, which means that the modification of font price can never be forgotten and the dealers make change to an older version, the change is still meaningful. To overcome these version problems, Dynamo uses several techniques. I will describe key techniques one by one and show you all steps in this phone market example. First, Dynamo uses vector clock. The vector clock is the data with a node with a pair, and the pair has node and the count number. If the write operation is handled by the same node, it will increase the count number. If the write operation is handled by a different node, it will add a new pair. Due to the asynchronous replication, we may have the different vector clock from the same previous vector clock. When the read operation has read both these two nodes, Dynamo will know that, oh, it's time to reconcile, and it will have a new version and new vector clock. Users always use website to send a GET or PUT request. After the HTTP, there are two ways. One way is by the load balancer. It will send request to a node. If the node is not in the preference list, it won't work and it will send the request to the coordinator. But if we have a client that it is partition aware, it will just directly send the request to the coordinator, and the coordinator is a node to handle the GET or PUT operations, and it's always the first node in the preference list. Dynamo also uses votings, and the read or write numbers depends on the designers, which is also an advantage of Dynamo. When the coordinator receives a PUT request, it will first write locally and send the request to n nodes. If W-1 node says that they can be written, it is a successful PUT request. Why W-1 is because it has been written locally, so the total number of W is W. And then the n-w nodes will be replicated asynchronously. When the coordinator receives the GET request, it will send it to n nodes. If R nodes responds that they can, if R nodes responds, it is a successful GET request. But the problem is that if the R nodes have different versions, which version is the correct version or how to reconcile these different versions. There are two ways. The first way is that the coordinator can reduce the causal relationship by itself and then send it to the client. Because the client is more familiar with the business logistic, it can help us reconcile and turn back a new merged version to the coordinator. And another way is just left right wing. In the paper, it says that in general, Dynamo uses the second strategy left right wing because although the first strategy is more accurate, it will waste a lot of resources. The following content is about how Dynamo uses in our phone market example, but due to the time limitation, I can't display it. But it can help you to put all previous techniques together and have a clear view about how it runs. And it is also important to show that the different parameter of RWN will give you total different.
Now, I will introduce a real-world example about the Dynamo. Fruit Ninja, which is a famous mobile game around the world, and it has millions of players. Obviously, Dynamo is one of the most important technologies in this game. There are three significant advantages of Dynamo in Fruit Ninja. The first one is stable. Performance will remain stable regardless of the size of the gamer. Dynamo maintains predictable low latency performance at any level of scale. If everyone's games are sensitive to latency and need to face millions of players, this feature will become critical. With Dynamo, game developers no longer have to waste any effort on performance tuning. And the second one is atomic increment. In addition to put and get command, Dynamo also supports atomic increments. This mechanism is very useful in the update process after the value has changed, because multiple requests from the application do not conflict. It is this situation that causes most of the progress lost in online games. If the player picks up 100 gold coins, you can directly ask Dynamo to automatically add 100 gold coin increments atomically without having to go through the process of getting records, adding coins, and returning them to Dynamo. And the last one is cost effective. Can we really support thousands of players at the cost of a cup of coffee a day? Yes, we use the example of saving games to estimate costs. Suppose the game has an average of 100,000 players per month, and most of them won't log into the game at the same time. So we roughly estimate that 1/10 of them will be online at the same time. In addition, we assume that the 10,000 players save the game every minute, and each player's progress data record is less than 1 kilobyte. Finally, we assume that each player needs to read the game state from the database every minute during the game. Since there are 60 seconds in a minute, our Dynamo must be able to support 167 writes and reads per second. Most organizations retain a portion of the buffer capacity, so we increase the read and write acceptance to 200 per second, while the total storage is set to 50 GB. Based on current US East 1 regional resources billing standards, such resources will only cost around $4 per day. In other words, the price of a cup of coffee of a day can fully support 100 players. The following graph is the Dynamo in the architecture of the Fruit Ninja. According to the manager of this game, they said Dynamo's cost savings are achieved by efficiency and ease of use, as well as significant reductions in maintenance costs. It has been very difficult to build, maintain, and split large real-time data-centric projects. The creation and maintenance of projects has also required the participation of a large number of technicians. However, in Fruit Ninja, with the help of Dynamo, we only need 2 server engineers. That's all. Thank you.